तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we continue our discussion on inventory models, and we begin by considering inventory models with discount. Let us go back to the first example, a single item model with annual demand of 10,000, order cost of rupees 300 per order, unit price rupees 20, interest rate at 20 per annum. So, here we will be using CC equal to I into C, which will work out to be the same rupees 4 per unit per year. The economic order quantity Q is given by root of 2 into D into C naught by Cc, which is 1224.75, and the minimum cost of ordering and carrying at the economic order quantity Tc is 4898.98. We have already seen this example and these numbers. Now, since we are placing an order at a time of 1224.75, and we assume that we are going to place several orders to meet this demand of 10,000 and more, we could ask the supplier for a discount. So, let us assume that the vendor or the supplier is willing to give a 2% discount on the unit price if the order quantity were 2,000 or more, and give a 4% discount if the order quantity were 5,000 or more. So, let us evaluate whether these two price break are favorable to us. Now, without any price break, at the existing price of rupees 20, at the economic order quantity, the total cost including the item cost would be 4898.98, which is obtained from this, plus the cost of the item, which is 10,000 items into rupees 20, which would give us 204898.98 rupees per year. Now, if we look at an order quantity of 2000, then at 2000 we avail a 2% discount. So, the number of orders will be 10,000 divided by 2000, 5 orders in the year, multiplied by ordering cost 300. Average inventory will be 2000 divided by 2, which is 0.5. So, 2000 divided by 2 into the carrying cost, which is 0.2 into 20, which is 4 rupees, plus the cost of the item, which is 10,000 items into 20 per item into 0.98. There is a 2% discount at the price break of 2000. So, what happens is this 2% discount gets reflected in the unit price as well as in the carrying cost. So, the unit price now becomes 20 into 0.98 because of the 2% discount into 10,000 items. The carrying cost, Cc being defined as I into C, I is 20% and C is 20 rupees. Now, the unit price is not 20, but 20 into 0.98. So, Cc is not 4, but Cc is 0.2 into 20 into 0.98. So, average inventory is 2000 by 2000 into Cc, which is 0.2 into 20 into 0.98. So, this works out to 201420. Now, when the order quantity is 5000, we get a 4% discount. So, we evaluate the total cost for an order quantity of 5000. So, order quantity of 5000 means 2 orders in the year, 10,000 by 5000 into 300. The carrying cost is 5000 by 2 is the average inventory. Cc is now 0.2 into 20 into 0.96. 0.96 comes because of the 4% discount. So, the unit price is not 20, but 20 into 0.96, which is 19 rupees and 20 paise. 20% of 19 rupees and 20 paise is the carrying cost per unit per year. Unit price of the item is 10,000 items into 20 rupees into 0.96. 0.96 comes because of the 4% discount. So, this total becomes 202200. Total cost including the item cost is minimum. Comparing the 3 at the economic order quantity, the total cost is 204898.98. At a 2% discount with order quantity 2000 is 201420, and a 4% discount at an order quantity of 5000 it is 202200. So, among the 3 values, the minimum value is 201420. So, total cost including the item cost is minimum when we avail a 2% discount at an order quantity of 2000 units. So, whenever we have a price break, we need to look at the total cost at the economic order quantity and the total cost computed at the price break points. In all the discount problems, we will include the item cost because the unit price now depends on the order quantity. Till now in all the models, we had not included the cost of purchasing the item. Only in discount models we use that because the unit price depends on the order quantity. It is enough to evaluate only at the price break. For example, the problem says there is a 2% discount if the order quantity were 2000 or more. Now, should we evaluate the total cost at some other order quantity which is higher than 2000? The answer is it is not necessary. Similarly, when we are looking at a 4% discount, we would get this 4% discount if the order quantity were 5000 or more. Now, the question is it necessary to evaluate at a 4% discount any order quantity more than 5000? The answer is no. It is enough to evaluate only at the price break, the point at which we get the discount, because for all order quantities other than those at the price break or for any order quantity which is higher than the price break, the cost will only be higher because of the quadratic nature of the cost function. It is also assumed generally that all price breaks will be for order quantities higher than the economic order quantity. For example, in this problem the economic order quantity was 1224.75. We did not assume any discount at the EOQ or economic order quantity. We assumed that there is a discount at quantity 2000 and 5000 which are higher than the economic order quantity. So, at any point whenever the discount is for quantities higher than the economic order quantity, it is enough to evaluate the impact of the discount only at the points at which there is a price break. If there is a price break at a quantity less than the economic order quantity, then it is accepted and evaluated at the EOQ for comparison with other price break options. Discount that gives minimum total cost is always chosen. We have not considered the case where, for example, there could be a 1% discount if the order quantity is more than 1000. So, if the vendor is willing to give a 1% discount for order quantity greater than 1000, then we will avail the 1% discount not at 1000 but at the economic order quantity. So, wherever there is a discount which fits into the economic order quantity, we will evaluate it at the EOQ. When there is a price break for quantities higher than the economic order quantity, we will evaluate the total cost at the point at which there is a price break, and that is what is shown here. Now, if there is a price break at a quantity less than the economic order quantity, then the price break is accepted not at the point at which there is a price break, but at the economic order quantity. Then such a TC, total cost, is compared against other discount points such as this, and whichever is minimum is always chosen. So, this is how we address problems with discount or price break. What we have to keep in mind is, whenever we are addressing inventory models with discount, it is absolutely necessary that we also include the total cost of the items, simply because the unit price now depends on the economic order quantity. It is not a constant anymore, it is a variable. it depends on the quantity that is being ordered. Therefore, all discount problems will include order cost, carrying cost as well as the cost of the item. This is one change from the previous models where we did not explicitly consider the total cost or price of the items. Now, let us consider a few more models in inventory, and we look at multiple item inventory model. So far we have seen in all the 5 models and examples, we have seen a single item model. Now, in the remaining couple of models that we will be discussing, we will look at multiple items. So, let us consider 2 items, we call them items 1 and item 2 with the following data. The annual demand D 10,000 for the first item and 20,000 for the second, order cost is 300 and 300, unit price is 20 and 25, and interest rate is 20% for both. Now, we have kept the order cost same for both these items, we have also kept the interest rate same for both these items. Now, carrying cost CC is expressed as interest rate I into C. So, carrying cost will be rupees 4 for the first item and rupees 5 for the second, but the interest rate I will be the same. Now, in all multiple item problems, it is customary that we keep the order cost same as well as the interest rate same. Interest rate being same is understandable because it is the interest that is paid on the money that is borrowed. Now, no matter whichever item that money is spent on. Order cost is kept constant because sometimes one can argue that order cost could be different for different items, because some items may require more intense inspection, some items may not. The cost of transportation could be different for different items and so on, but in all these multiple item problems, it is customary to assume that order cost is the same. The reason being, it would be very difficult for the organization to go back and compute an order cost for every item. So, what the organization would do is, over a period of time, they will find out what is the total amount spent on ordering for all the items, and then average it out with the number of items ordered, and we get one average figure which is the representative order cost for all the items. Therefore, we choose the same 300 as the order cost for these items. Now, going back to the first model, we find out the economic order quantities for both these. We already have the result for item 1. So, for item 1, the economic order quantity is 2 D1 C0 by IC1. We use subscript 1 for item 1 and subscript 2 for item 2. So, Q1 star economic order quantity for the first item is 1224.75, corresponding total cost is 4898.98. Number of orders per year would be D1 by Q1. Total demand is 10,000, economic order quantity is 1224.75, number of orders is 8.16 orders per year. Considering the second item, we compute Q2 star economic order quantity for item number 2 as root of 2 D2 C0 by IC2, which works out to 1549.19, and the total cost TC2 7745.97. Number of orders for the second item is given by D2 by Q2, which is 12.91. If we consider these two items, now we observe that together we place 21.07 orders per year for these two items put together. Because the number of orders are different, the points in time where these orders are made are also different, so we make 21.07 orders per year. In practice, when we look at more than 1000 items in a factory or in an organization, each has a unique order cycle resulting in a very large number of orders. Now, the organization might want to reduce the total number of orders to lessen the burden, though it might be uneconomical. It would be uneconomical because we have already seen that any quantity other than the economic order quantity would increase the total cost of ordering and carrying. So, it could be uneconomical, but the economic order quantity is now posing a large burden on the people who are doing the purchasing. Therefore, the organization might want to reduce the total number. Let us assume that we would restrict to 15 orders for the above two items together. what was 21.07 orders per year, we would assume that we want to reduce the burden, therefore we are going to restrict it to 15 orders, and the number 15 is obviously smaller than 21.07, so that the burden is reduced. Now the problem would be, now for these two items put together, sigma C naught is constant dj by qj plus sigma I into qj cj by 2. Now I cj is the carrying cost, C naught is the order cost, dj is the demand for the item, and so on. So for j, for many number of items we could sum it up. For 2 items we could write it as C naught into d1 by q1 plus d2 by q2, and so on. The constraint now will be sigma dj by qj is less than or equal to n. Now this capital N is 15, the restriction that we have. Dj by qj will be the number of orders per year for item j. So sigma dj by qj is the total number of orders for these two items put together should be less than or equal to 15, qj greater than or equal to 0. Now the objective function is now the sum of the total ordering cost and carrying cost for all the items. The constraint will ensure that the total number of orders is restricted to a fixed number n. We assume in this case, which is also true, that the constraint is violated by the individual economic order quantities. The constraint said n is equal to 15, together these two items have 21.07. So the constraint is violated when we substitute q1 star and q2 star. Now we want to solve this. If the constraint is satisfied by the individual EOQs, then the individual EOQs are optimum to the problem. For example, if we had said that this n is 25, if we had said we would like to restrict it to 25 orders per year, then we are happy doing 21.07 at the economic order quantity. Only when the constraint is violated, the problem becomes significant. Now when the constraint is violated by the individual EOQs, we can easily show that the constraint will be satisfied as an equation, not as an inequality, when we actually solve the constrained version of the problem. Even though this constraint is an inequality, now if the present solution is violating this constraint, and when we solve the problem with the constraint, now we can easily show that it is okay if we substitute this with an equal to sign and not solve it as an inequality. So we can convert this into an equation and solve. We do this because it is easier to solve nonlinear problems when the constraints are equations. The nonlinearity comes in the objective function because of qj being in the denominator, as well as in the constraint because qj is in the denominator. Constrained nonlinear problems, it is easier to solve with equations than with inequalities. In this case, because we know that if the constraint is binding, it will be satisfied as an equation, we convert the inequality to an equation and then we solve. So it becomes dj by qj equal to n. Now the problem becomes a nonlinear objective function with a single constraint, which is an equation in this case. Now we use Lagrangian multiplier technique. We introduce a lambda, which is a Lagrangian multiplier, and write the Lagrangian function. We take the constraint into the objective function and write the Lagrangian. So the objective function remains as it is. The Lagrangian has the lambda which comes in, which is the multiplier, into sigma dj by qj minus n. Now once the Lagrangian is written, the optimum values of qj and lambda can be obtained by equating the partial derivatives dou L by dou qj and dou L by dou lambda to 0. We are not going to explicitly evaluate the second derivatives and show that it is a minimum. For all inventory problems, it is assumed that the second derivative will indicate a minimum. So dou L by dou qj will give minus c naught dj by qj square plus I cj by 2 plus lambda dj by qj square equal to 0. Now this comes because there are 3 terms. This would give minus c naught dj by qj square, this would give I cj by 2, this would give minus lambda dj by qj square. So we have 3 terms equal to 0, from which qj star is root of 2 dj into c naught plus lambda by I cj. The square root is for the entire term. Dou L by dou qj or dou L by dou lambda equal to 0 would give sigma dj by qj equal to n. Now if we use this formula qj star equal root of 2 dj into c naught plus lambda by I cj, now we realize that we do not know the value of lambda. For a particular item j, the value of dj is known, C naught is known, I is known, Cj is known, but lambda is not known. Unless lambda is known, we cannot compute the economic order quantity Qj star. So, in order to find out this lambda, we go back and partially differentiate this with respect to lambda, which would give us sigma dj by Qj equal to n. So, that is written here, sigma dj by Qj equal to n. Now, we go back and substitute here sigma dj by Qj equal to n. Qj we go back and substitute Qj star equal to root of 2 dj into C naught plus lambda by ICj. So, we substitute for this Qj from this and we get an expression like this, sigma dj by root of 2 dj into C naught plus lambda by ICj equal to n. Now, we can simplify this, we can pull out the C naught plus lambda outside, dj and Cj are only dependent on the item j. So, we can pull out C naught plus lambda and 2 outside of this, then we have sigma root of dj Cj, because there is a dj term here, there is a root of dj term here and there is a root of Cj term here. So, it will simplify itself to give us root of dj Cj. So, finally, on simplification we would get lambda equal to I by 2n square into sigma root of dj Cj the whole square minus C naught. So, we have a nice solution here with lambda given by this quantity. We know all the terms here, we know n, we know dj, we know Cj, we know C naught and I, we can calculate lambda, and once we calculate lambda we can go back and calculate the economic order quantities Qj star. Now, for the same example we can show that when we substitute n is equal to 15 here, n is equal to 15, rest of the things are known, I is 0.2, 20%, for the first item dj is 10,000, Cj is 20, C naught is 300. So, we substitute for the, we get sigma dj Cj is here. So, d1 is 10,000, d2 is 20,000, C1 is 20, C2 is 25. So, we substitute here and we get lambda is 292.20. Now, once we find out lambda, we can go back and get the economic order quantities Q1 star and Q2 star, 2 d1 into C naught plus lambda by IC1, Q2 star is root of 2 d2 C naught plus lambda by IC2. So, they become 1720.76 and 2176.607 respectively. Now, to verify, we go back and find out n1 plus n2 number of orders, we get exactly 15. We have solved with 15, we have solved for n is equal to 15, we have solved for n is equal to 15. So, total number of orders becomes 15. Now, the order quantities now increase. Previously 1224.75 and 1549 have now gone up to 1720 and 2176. This is because the restriction on the number of orders will try to increase the order quantity. Now, total cost also goes up to 13,383.04. Individual TCs are also higher than what it was. Any constraint problem minimization would always give a higher value to the objective function than the unconstrained problem. So, the total cost increases, order quantity is increased, but the total number of orders now becomes exactly 15. Now, we observe that because of the restriction on the number of orders, the individual order quantities have increased. We can also observe this, the new Q1 star by Q1 is 1720 by 1224.75, which is 1.405. The new Q2 star by the old Q2 economic order quantity Q2 is 2176.607 by 1549.19, which is 1.405, which is the same as n1 plus n2 by n, originally without the constraint 21.07 orders, with the constraint 15 orders, same 1.405. Either we can solve the problem optimally by using the Lagrangian multipliers, get the values for lambda, go back and substitute, or we can simplify this, use this as an approximation to quickly get the values of Q1 star and Q2 star. Because we know n1 plus n2 21.07, we want to bring it down by 15, so the factor of 1.405, So, multiply it with a factor of 1.405 to get 1720.76 and 2176.607. So, this could be used as an approximation as well. Now, when the constraint is violated by the EOQ, we observe that lambda is strictly positive and roughly of the order of C naught. See, lambda was 292.20, which is roughly of the order of 300. For example, we won't get lambdas like 0.1 and so on. So, we will have high values for lambda, which is of the order of C naught. Strictly positive value indicates that the constraint is violated by the economic order quantities. This Lagrangian method should be used only when the constraint is violated by the EOQs. We have already seen that. For example, if we had directly used the equation to find lambda for n equal to 25, we would get a negative value of lambda. Now, we had already seen that it is a less than or equal to condition. In case instead of 21.07 we said 25, we will be happy to order the EOQs and the constraint is satisfied. So, we should use this model only when this constraint is violated by the economic order quantity. If we still blindly use the lambda equation, which we have here, if you blindly use the lambda equation and try to solve it for n equal to 25, then we will get a negative value for lambda. This negative value for lambda implies that the constraint is actually satisfied by the EOQ. There is absolutely no need to have used the value for lambda. The negative comes because we had forced an inequality to an equation. So, it will try to solve it as an equation and give a negative value, because in the Lagrangian method we are forcing the constraint to be an equation. So, the Lagrangian method should be used only when the constraint is violated. When the constraint is satisfied by the EOQ, the optimal order quantities remain unchanged, but this method will force the Qj to satisfy the constraint as an equation and give a negative value for lambda. Now, what are the steps? Solve the unconstrained problem and get the values of Q star, like what we did. We solved the unconstrained problem first and we got the values of the economic order quantities, which are these: 1 total cost and the number of orders. Then go back and check whether the constraint is satisfied or violated. Now, we found out 21.07 orders which violates the 15, then use the Lagrangian to solve. So, the model is constraint is satisfied, existing Q star EOQ are optimal, use the Lagrangian multiplier method only when the constraint is violated. Now, let us look at a different kind of a multiple item model. Now, we look at the same problem here with the same economic order quantities: 1224.75, 4898.98. Average inventory value. What happens is, when we order 1224.75, the maximum inventory in the system is 1224.75. The average inventory is Q by 2. Now, that much of average inventory is held right through, which means a certain amount of money is being locked up in the inventory. So, money value or the average inventory value is Qj Cj by 2 or Q1 by 2 into C1, which is 12,247.5 in this example. And for Q2 star, for the second item, the Q2 star is 1549.19 into 25 by 2 would give 7745.97. So, average inventory value Q2 C2 by 2 is 19,364.88 for 1549.19. 1549.19 divided by 2 into rupees 25 would give us 19,364.88. So, both the items put together have a total value, money value of average inventory of both these items is 31,612.38. Now, as we saw in the previous example, we have many items, say more than 1000 items in a factory, each has a certain inventory, resulting in a very large amount of money locked up in goods or stocked in goods. Organization might want to reduce the total money value of the inventory to lessen the burden, and let us assume they want to restrict it to 25,000. Now, the money value for these two is 31,612, we want to bring it down to 25,000. So, we have the same objective function to minimize the total of the ordering cost and carrying cost, subject to the condition Qj Cj by 2 less than or equal to B. This is the money value of the items, this is the restriction, this is the 25,000, that we have, this is the money value of the items at an average locked up in inventory, Qj greater than or equal to 0. Once again we realize that this constraint is violated, and when this constraint is violated, it can be solved as an equation. Objective function is the sum of the total order cost and carrying cost. Constraint ensures that the fixed amount B is met. We assume that individual economic order quantities violate this constraint, convert it to an equation, and then solve it as we did in the previous case. So when the constraint is violated, we could convert it to an equation. Sigma C Qj Cj by 2 is equal to B. Now we have a nonlinear objective function with a linear constraint. Constraint is only on the money value of inventory, so Qj appears in the numerator, so we have a linear constraint. Objective function is nonlinear because order cost component has Qj in the denominator. So the Lagrangian function is given by sigma C naught into dj by Qj. Dj by Qj is the number of orders, C naught is the individual order cost, so dj by Qj into C naught is the money value of the order cost per year. Qj ICj by 2 is the inventory carrying cost, ICj is the inventory cost, and lambda is the Lagrangian multiplier. The constraint Qj Cj by 2 equal to B is taken into the objective function. The Lagrangian function is created by introducing a multiplier lambda, which is multiplied by sigma Qj Cj by 2 minus B. Now once again we have to find the optimum values of Qj and lambda, and these are obtained by equating the partial derivatives dou L by dou Qj and dou L by dou lambda to 0. Dou L by dou Qj equal to 0 gives minus C naught dj by Qj square plus ICj by 2 plus lambda Cj by 2 equal to 0. Now this would give a minus C naught dj by Qj square because Qj is in the denominator. Here Qj is in the numerator, so you get ICj by 2. Here again Qj is in the numerator, you get lambda Cj by 2 equal to 0, from which Qj star is root of 2 dj C naught into I plus lambda into Cj. Now we can calculate this Qj star only when the value of lambda is known. Right now we do not know the value of lambda. Now to find out the value of lambda, we partially differentiate with respect to lambda and get sigma Qj Cj by 2 equal to B. So we substitute for this Qj from here, root of 2 dj C naught into I plus lambda Cj. Now to get the optimum value of lambda, we substitute for Qj star in this to get, now this sigma root of 2 dj C naught into I plus lambda Cj into Cj by 2 equal to B. This on simplification would give lambda equal to C naught by 2B square sigma root of dj Cj the whole square minus I. So one needs to simplify this expression to finally get this value of lambda. Now for the 2 item example, when we substitute B equal to 25,000 in this and all other values known, C naught is 300, sigma dj Cj root of dj Cj can be calculated, D1 is 10,000, C1 is 20, D2 is 20,000, C2 is 25, I is 0.2. So we substitute all these values, we would get lambda equal to 0.12. Now here we realize that lambda is roughly of the order of I is 0.2, so lambda is roughly of the order of I. Now Q1 star is root of 2 D1 C naught into I plus lambda C1, 968.5647. Q2 star is root of 2 D2 C naught I plus lambda C2, which is 1225.148. Verifying Q1 C1 by 2 plus Q2 C2 by 2 would give us exactly 25,000. We have solved this problem for B equal to 25,000. Sigma Qj Cj by 2 is 25,000. Now total cost for this will increase. 12,994.73 is higher than the economic costs, higher than it's higher than 4898.98 plus 7745.97. So with the new values, the total cost would be higher, 12,994 is higher. The individual order quantities have come down they have come down because of the restriction on B equal to 25,000, and because they have come down, the total cost goes up. We observe that because of the restriction, the individual order quantities have decreased and the total cost has increased. We also observe something which we did very similar to what we did in the previous model, where the new one divided by the old one is 968.5647 divided by 1224.75, which is roughly 0.7908. Similarly, Q2 star by Q2, the new 1225.148 divided by the economic order quantity 1549.19 is also 0.7908. Now the budget was restricted to 25,000, previously it was 31,612, dividing one by the other we would get 0.7908. Now once again these approximations can also be used to get the new values very quickly. Now this 25,000 is known, 31,612 is known from the economic order quantity, dividing one by the other 0.7908 is known. So go back to the old economic order quantity, multiply by 0.7908, you will get the new value of Q1 star. So either we can go back and use the Lagrangian and solve it, or we could approximate it by this simple term. Once again we need to use, or we can use the Lagrangian model only when the constraint is violated, and lambda will be strictly positive roughly of the order of I when the constraint is violated. Strictly positive value of lambda indicates that the constraint is actually violated. Once again the method should be used only when the constraint is violated by the EOQs. If we had used it for B equal to 35,000, now let us go back here. Now we had 31,612, now we placed restricted B to 25,000. If we had put B equal to 35,000, then the economic order quantity satisfies the budget restriction, therefore the economic order quantities themselves will be optimal. However, if we make the mistake of evaluating lambda for B equal to 35,000 and use this expression, we would get a negative value of lambda. A negative value of lambda indicates that we will get a negative value of lambda indicating that the constraint is actually satisfied by the EOQs. Once again this is because the Lagrangian method, we are forcing the constraint to be an equation and we are solving it. So this is how we solve the budget constraint inventory problem. Now let us look at one more problem, which is a space restriction. So we again look at the same two items with the additional condition that there is a storage space that is required for each of these items, and say we represent it as some kind of cubic feet per unit. We assume that item 1 requires 3 units of space and item 2 requires 4 units of space. So at the economic order quantity we have Q1 star is 1224.75 and the space requirement will be Q1 S1 by 2, which is 1837.125 on an average. Q1 by 2 is the average inventory, so we calculate the space requirement only for the average inventory, not for the maximum inventory. This is because at any point in time not all items are going to be at their maximum levels, they are going to be at different levels of inventory, and an average is a very reasonable approximation for the present state of the inventory. So we compute the space requirement for the average, not for the maximum. Similarly, for the second item, the economic order quantity is 1549.19, TC is 7745 and the space requirement is 3098.38. Together the two items require 4935.505. Once again we argue that we will have many items in the factory, each requiring a certain amount of space, so we would like to minimize the quantity so that the available space can only be used. So we assume that we want to bring down this 4935.505 to 4000 cubic feet. Once again we have the same objective function with the constraint alone changing to Qj Sj by 2 is less than or equal to S. S is the restricted storage space of 4000, Qj greater than or equal to 0. Once again we can show that we can convert this into an equation and solve it using the method of Lagrangian multipliers if the economic order quantity violates this 4000. In our example, the economic order quantities require 4935.5, a restriction of 4000 is violated by them, so the constraint is not satisfied, by the economic order quantity. We now need to solve the constraint problem and get the new values of Qj star, and we can solve it as an equation because the constraint is binding. So we convert it to an equation as we have been doing right through, and then the constraint becomes sigma Qj Sj by 2 is equal to S. Now we set up the Lagrangian function, same objective function, sigma C naught dj by Qj, which is the total ordering cost, I Cj Qj by 2 total carrying cost of inventory, lambda is the Lagrangian multiplier, Qj Sj by 2 minus S, this represents the constraint. So constraint is brought into the objective function. Now once again the optimum values of Qj and lambda can be obtained by setting the partial derivatives to 0. You get minus C naught dj by Qj square plus I Cj by 2 plus lambda Sj by 2 equal to 0. This would, Qj is in the denominator, so you get minus C naught dj by Qj square, Qj is in the numerator, I Cj by 2, Qj is again in the numerator, get lambda Sj by 2, lambda Sj by 2 equal to 0, from which Qj star is root of 2 dj C naught into I Cj plus lambda Sj. Once again we can compute Qj star only if we know the value of lambda, and in order to find out the value of lambda we go back and substitute sigma Qj Sj by 2 equal to S. Now when we go back and substitute, we cannot get an expression for lambda as we did in the previous case, or we do not get a nice compact expression as we did in the two previous cases. In this case we have to substitute for various values of lambda and then find out whichever works for this constraint, and that value of lambda which brings the left hand side close to right hand side is the optimum value, unlike in the two previous cases. So we compute Qj Sj by 2 for various values of lambda, and we get for lambda equal to 0.669 we get 3999.77, which we think is reasonably close to 4000. So we stop with lambda equal to 0.669, which has a space requirement of 3999.77. Now the new values of Q1 star and Q2 star will be this. We have to substitute IC1 plus lambda S1, IC2 plus lambda S2 to get 999.41 and 1250.326. Because of the space restriction, the order quantities come down. Total space is 3999.77 and total cost would increase to 12,925.15. Now we also observe that because of the restriction in space, individual order quantities decrease and the total cost increases. Now you can also have an approximation once again as we had previously. So new value by old value of the order quantities gives us 0.816, Q2 star by Q2 gives us roughly 0.807, and the 4000 by the actual space taken by the economic order quantities also give us a 0.81. So we may assume 0.81 to be a reasonable approximation for this, and we can go back and get approximate values of Q1 star and Q2 star instead of taking the trouble of setting up the Lagrangian, getting this expression and substituting to get the best values of lambda. So if we want the optimal, we get this Q star expression, but to get the value of lambda one needs to go back and look at substitution, or one can alternately use this approximation. We know this 4000 and this 4935, so we know this fraction 0.81, go back and multiply the economic order quantities with that fraction to get the approximate values of Q1 star and Q2 star. Now when the constraint is violated by the economic order quantities, we observe that lambda is strictly positive and roughly of the order of, and lambda in this case is strictly positive. Now strictly positive value indicates that the constraint is violated by the EOQs, and the Lagrangian multiplier should be used only when the constraint is violated by the EOQ, otherwise it would end up giving us a negative lambda and so on. So we would get a negative value and so on. Now let us go back to the last model when we look at multiple items and multiple constraints. Now we could have a situation where we would like to have restriction on the number of orders as well as restriction on the inventory. For the same problem, let us assume that we have restriction on both these. We want to bring down the 21.07 to 15 as well as bring down the inventory. Now let us assume that we have restriction on both and the EOQs violate both these restrictions. Now when both these are violated, we will have an infeasible solution. This is because the number of order restriction tries to increase the order quantity, the inventory restriction tries to reduce the order quantity. At any point in time we can handle only one of them, and the economic order quantity is violating both, so we cannot have a feasible situation in case 1 when the EOQ violates both and there is a restriction on both. We will be able to satisfy only one of them. When we have a number of order restriction and space restriction, once again we have a restriction on both. EOQs, let us assume, violate both as in the examples that we have seen. Once again we will have an infeasible solution because the order restriction tries to increase the economic order quantity, space restriction tries to reduce the order quantity, they conflict each other, the EOQ is violating both, so we cannot have a situation which satisfies both these. We can handle only one of them and not both. We can have a case 3 where we have a restriction on inventory and space. This is possible. If we assume that we have restriction on inventory and space and the EOQ violates both, considering our own example, we looked at 25,000 and 4,000, and we considering only the inventory, we got these values 968.56, 1225.148 using the Lagrangian multipliers. Now the space requirement for this is 3903, which is okay, which satisfies this 4000. Therefore we assume that this is optimal. We cannot actually satisfy both. We will only be able to satisfy one, and the other will get, we will be solving for one and substituting in the other to find out which one works. In this case we have solved for inventory, and when we substitute the space works, therefore this is the optimum solution. We can handle two constraints only when both try to shift the order quantity in the same direction. Both the space constraint and the inventory constraint tries to shift the order quantity, reduce the order quantity. In this case both reduce, therefore we can consider. If for the same problem we had a budget restriction of 30,000 and a space restriction of 4,000, first we would solve for inventory. We would have got Q1 as 1162, Q2 is 1470 with a space requirement of 4683. So when we had solved for budget of 30,000, we find the space restriction is violated. So we go back and solve for the space 4000. We already know the answers 999 and 1250. Now we compute the inventory value for these, which is 25623, which satisfies. So when we have both, we first solve for one and substitute in the other. When the solution for one satisfies the other, we get the optimal. Normally the practice is, and for this problem the solution is 999.4172, 1250.326, inventory value of 25623, which is less than the 30,000 and it is okay. Space 4000 is exactly satisfied. Now it is customary that we start, when we have these two restrictions between the inventory as well as the space, it is easier to solve for the inventory because we know the expressions for lambda. So when we have a problem like this, we first solve for the inventory, and if the inventory solution satisfies the space, then we are optimal. But if the inventory violates, as in this example, then we have to go back and solve for the space and then go back and substitute in the inventory, which will eventually be satisfied. So only one of them will be the optimal solution to this. So with this we kind of end the discussion on deterministic inventory models. We sum it up by saying that we have looked at several aspects of deterministic inventory models. We saw the 4 basic models to find out the economic order quantity as well as the economic batch quantity for production. We then looked at the inventory models with discount, and then we looked at inventory models for multiple items with constraints, 3 types of constraints: constraints on the number of orders, constraints on the money value of inventory, constraints on the space. We solved all 3 of them individually, and then we also looked at combination and said that we can solve only the combination of inventory and space, and we worked it out through an example. Now at the end of this inventory, we come to the end of the first course on the fundamentals of operations research, and before we wind up, let us go back and try to give a summary of what we have seen in this lecture series on the course fundamentals of operations research. We have had 22 lectures as part of this first course or the introductory course on operations research. Now the course on operations research, we looked at 7 modules in this course. The course can broadly be divided into 7 modules the way we have addressed the fundamentals of our course. The 7 modules are linear programming problem formulations, linear programming solutions, duality and sensitivity analysis, transportation problem, assignment problem, dynamic programming and deterministic inventory models. So these were the 7 modules that we addressed, and if we go back and try to recapitulate what we saw in each one of these, the linear programming formulations introduced the topic to us. We saw multivarious formulations, we saw 4 distinct examples of formulations. We saw how to formulate a real life situation into a linear programming problem. We saw maximization and minimization objectives. We defined the terminologies objective function, constraint, decision variable. We saw how to write the objective function, 2 types of objective functions, types of constraints such as inequalities, equations, inequalities with greater than equal to, less than equal to equations, types of variables such as greater than or equal to, less than equal to and unrestricted. We saw enough examples to illustrate the various types of objective functions, types of constraints and the types of variables. In this course then we moved to linear programming solution. We saw 3 methods to solve linear programming problems. The graphical method, which was applicable for a 2 by 2 problem or a 2 variable problem, which could be represented in a graph irrespective of the number of constraints. Then we looked at the algebraic method, which is an improvement because it could handle multiple variables, and then we saw the limitations of the algebraic method, and then we introduced the simplex algorithm both in algebraic form as well as in tabular form as a method which is superior to the algebraic method. We also saw the various aspects of simplex. We saw the various aspects such as initialization, iteration and termination, how to construct or initialize the simplex table, what happens during iteration and what are the termination conditions. We saw also the big M method when we solved a minimization problem, particularly problems with greater than or equal to constraints. We saw aspects such as degeneracy, alternate optima, unboundedness and infeasibility, and defined the termination conditions for linear programming problems. Then we looked at duality and sensitivity analysis. We introduced the dual. We saw a mathematical expression to the dual. We also saw the physical meaning or economic meaning of the dual, economic interpretation of the dual. We also looked at some duality theorems, and we also showed that the simplex algorithm satisfies or solves both the primal and the dual, and it is an example of a primal algorithm where it always keeps the primal feasible, and when the dual becomes feasible becomes optimal. We also looked at the economic interpretation. We also saw the dual simplex method, which is another variation of the simplex algorithm, which is used to solve particularly minimization problems with greater than or equal to restrictions. Under sensitivity analysis, we looked at what happens to the problem when there are changes in the coefficients. We looked at 7 aspects in the sensitivity analysis: changes in the objective function coefficient of a non-basic variable, changes in objective function coefficient of a basic variable, changes in the right hand side values, changes in the constraint coefficient of a non-basic variable, adding a new product or adding a new variable or adding a new column, they all mean the same, adding a new constraint, adding a new row, which also means the same. So we looked at these 7 aspects, and finally we said that if there is a change in the constraint coefficient of a basic variable, then we do not use sensitivity analysis and solve the problem all over again, because the matrix B would get affected by such a change. If the change is such that the B inverse is not affected, then it is good to do sensitivity analysis, and sensitivity analysis is useful under those circumstances. Now these 3 modules in some sense is the entire linear programming portion of the course. Modules 4 and 5 looked at transportation problem and assignment problem, which could be formulated and solved as linear programming problems. They are formulated as linear programming problems, but both are not solved using the simplex algorithm directly, but they are solved using algorithms which have all the properties and characteristics of the simplex algorithm. So, we formulated the transportation problem, we showed that it is a linear problem, and then we said we could solve the problem faster and better compared to the simplex, and we said there are two aspects of solving the transportation. One is to get a good basic feasible solution, and then to try and improve this basic feasible solution to get to the optimal solution. We looked at three methods: northwest corner rule, minimum cost method, and Vogel's approximation method to get the initial basic feasible solution. We also looked at the we looked at the stepping stone method and the UV method to solve the transportation problem optimally. We also solved some degenerate cases of transportation problem to show what are all the possibilities that can happen when one tries to solve transportation problems. We then moved to the assignment problem, which is a special case of the transportation problem. We explained the Hungarian algorithm that is used to solve the assignment problem, and we also showed in the how the Hungarian algorithm is optimal and why we need a special algorithm to solve the assignment problem, even though it is a special case of a transportation problem. We then moved to a different aspect called dynamic programming. Dynamic programming problems were different from the problems that we encountered in the first 5 modules. Dynamic programming is a very special part of operations research, where we solve the problem by defining the stage, state, decision variable, and criterion of effectiveness. We solve the problem at various stages, one variable at a time, with a dependency being modeled through the use of state variables. We saw different aspects. We saw problems where the decision variables took discrete integer values, where they took continuous values. We saw situations where we maximized, minimized. We used calculus to find out the first derivative. There were situations we used linear functions and evaluated the function at the extreme points. We also, through 2 examples, we attempted to show how integer programming problems and linear programming problems can be solved using dynamic programming. Last, we addressed the deterministic inventory models, and we saw 9 different models to cover the various aspects of inventory, including economic order quantity, economic batch quantity, discount, and multiple item models. So, these 7 modules and the topics that we covered would kind of take us through a first course in operations research. There are other topics which are covered under the fundamentals of our course, but we are going to restrict ourselves only to these 7 modules. There are many more topics that are there in this field of operations research. It's a very vast field with many tools and techniques available. There are other topics that have to be studied, topics such as advanced topics in linear programming, methods like how to handle bounded variables, decomposition algorithm, column generation methods, goal programming that looks at multiple objectives, and so on, and how to efficiently invert a matrix, and how to make the simplex algorithm better and faster. What are the various other aspects of linear programming in terms of its complexity? So, all these have to be studied. We will have to cover additional topics such as integer programming, combinatorial optimization, network models, nonlinear programming, game theory, queuing theory, and so on. So, all these also need to be covered as topics of operations research. All these topics have not been covered in this first course that we have seen in 22 lectures. Now, we need to look at all these aspects as well. Topics such as integer programming, network flows, traveling salesman problem, queuing theory, quadratic programming, nonlinear programming are all usually covered in the advanced operations research course, and they have not been covered, they have been left behind in this course. So, with this we essentially come to the end of our treatment of the first course in operations research with these 7 modules, and we look forward to another course, advanced operations research, which is handled separately. We hope you benefit by viewing this and listening to whatever we have covered in 22 lecture hours. You are also free to give your feedback to the people who have made this possible. Thank you.